Hey, Cyprien here. Let me show you today how to understand the results that come out of a simulation with OnScale if you do a PMUT analysis. So this is, you have a PMUT here which fires some waves into water, for example air, and you have an object here and you want to know basically what is the distance in between this PMUT and this object. So a PMUT, if you don't know what it is, it's an ultrasonic type of sensor which is based on a MEMS device. So you have a small membrane which vibrates and generates acoustic wave into the medium. Okay, so you get this type of result after a slight post-processing. So let me just show you what you get when you actually open your results and how you can understand what you actually get. Very quickly, let me come back to the model. So this is the model I'm showing in this video. The model is available on OnScale website for download. So it is a 2D axisymmetric of a PMUT device which fires into let me check what is this material. Geometry. Okay, so this one, it's water. Okay, it fires into water. And here I put an object here, and I want basically to simulate a wave here, so I'm applying a voltage. This vibrates, this generates acoustic waves, and I have 3 probes, 1, 2, and 3 as the outputs. So different type of output. I have time history, displacement, so that's not the one that I'm interested in. I have time history, acoustic pressure. So this is the output number 3, which is in the middle. I have another time history acoustic pressure, so this one is just here at the position of my object. I want to know the distance. And this one here, the last one, is the measure of the acoustic pressure just at the PMUT boundary. Okay, now I calculate all that with OnScale. So you'll see all that in another video, how I do the modeling and how I get those results. This video is about how to analyze your results. So once you calculate all that, you should get FLX data, FLX history, and snapshot. So the FLX data contains the maximum acoustic pressure. The snapshot contains the acoustic pressure following to a certain time step calculated that I set up, and the time history FLX history data contains some acoustic pressure curves. So you have 2, 3, and 4, and this corresponds to, so the first one is the middle position, if you remember. Let's reset the middle one. This is the result of acoustic pressure at just before my obstacle, and the last one is at the input. So it looks a very similar curve, but if you look at the amplitude, there's a huge difference here. This at the output of the PMUT, the amplitude is huge, it's like almost 3 million. And so this is a pressure, right? So this is PA. So yeah, it's like 3 MPa, if I'm correct. No, yeah, right, 3 MPa. Now if I just this one, you see that the amplitude decreases a lot. So if I print out several curves together, basically you can compare. So the first one, this is amplitude at the middle, and this is the amplitude at the obstacle. Okay, so it's quite difficult to understand actually what you are getting out of this. So let's have a look at the graphical. What happens graphically to this? And for that, let's have a look at my acoustic pressure and how it evolves with time. So this 2D axisymmetric model. So so here it's half of the model, and my PMUT is here in red. It vibrates. You have some air here, and this is water. and this is my obstacle, and you want to see the wave going from here to here, basically. Now, the thing is that you have this option to plot data over time, and you can, like that, see what happens. But if you do that, you just see nothing, you just see color changing, and you don't know what's happening. So why do you have that? It's because of the auto scaling of the color bar. Yeah, it sounds a bit stupid, but you don't see anything in the water. That's because the pressure here inside the PMUT is huge. So basically all the colors are kind of concentrated around this area, and basically everything you want to see is inside this color range here, and you don't see anything because everything is in the same color. So what you have to do is to check this option, user defined data range, and then you just want to cut all this range of color to this. So I just put I think, let's say 4. Let's see if I start to see something. Oh, and now you start to see some wave here, right, going on inside. Let's even do it better. Let's do I don't know, 3. Yeah, now it's even more obvious. And now I just fix the data range. So if I come back to the beginning and I just go step by step through what happens, you actually see the acoustic pressure which starts to build up and propagate inside your water. So that's much better than what I saw at the beginning. So you see the acoustic pressure propagating here and reaching this obstacle, and the curves I was showing you here are basically the measure in amplitude of this. So, and what I would like to show you also is that basically how do you calculate the time which this pressure waves get from here to here. It's a bit tricky actually, because well, you can do it pretty easily if you just take a calculator or an Excel file and you just print out the data which get out of this curve. Now, to see that in the post-process, it's a bit more tricky. So let's just print together this model and the time function curve at this position here. So this is this one, the T24. Sorry, check this. Double click, okay. And let's zoom on this part of the signal, yeah, like that. Okay, so now I have maybe a bit more like this. Okay, now I have some idea more or less of what happens to, okay, like that, better. What happens to my signal at this position, and it's not very well. Let me, okay, do like that. Okay, I think this is, no, this is not, let me check. I want, this is the input signal, right? Oh, this is the input signal. Okay, this is not the one I want to show you. Let's just reset this viewport. Okay, the one I want to show you is this one. Yeah, this is the one at this point here. You can recognize by the amplitude actually of the signal, because the amplitude is much smaller than the other one. So, and now you basically see, you start to see acoustic pressure building up at this time, which is basically so 10 minus x, 0.1 microseconds. If I'm not telling you, yeah, I think 0.1 microseconds. So that's when you start to see pressure appearing. And I want to see, does it correspond to actually what I have visually here? So for that, let's take a look at okay, let's take a look at what happens here. You see that the wave propagates, and this part here and this color here it basically, well, okay, let's say now. So now you have a signal reaching this, so I should start to see something around this. So how do I know this frame? So here it's written showing frame 24 on 250. That's because basically I divided the whole time scale into 250 time steps, and now I'm looking at the 24th time step. So if I want to know what time this corresponds, I have to know the total simulation time, and I have just basically to multiply by 24 and divide by 250. So it should be actually written somewhere. They should indicate, you know, what time step I'm looking at and what is the time value here, but I just can't find this simple information. So let's just do that. Let's go back to designer. Let me look just at what time. Okay, the total simulation time is basically 1 microsecond. So that's the total simulation time, 1 microsecond. And now I'm looking at 24. So let's just open a quick Python notebook, and let's just make some quick calculations. So you see that I already did some stuff. Let's just calculate again. 24 multiplied by total time. So I call this TT. So this is the total simulation time, and I'll just divide that by 250. Okay, so this is the time value at this time step, 9.6. So almost 0.1 microsecond. So if the time step that corresponds to this is around here. So what I'm looking at now in this distribution here at this point is here. So you see that it corresponds from this pressure to this curve, and if I just continue to visualize that, the acoustic pressure just increase here. Now, why am I actually doing that? Because the purpose of this kind of sensor is just to measure the distance between the sensor and the obstacle. So you want to know when the waves comes back to this, and if to know that, let's reset the viewport and let's look at the. Let's look basically at. Okay, so this is the input. This is the acoustic pressure at the input, and you see that you basically get some periodic kind of data. So if you compare the peak at this signal here and with the peak at this signal, you get basically the time in between a back and forth of the wave. So to calculate this, what is actually the distance? Well, you have to use a very basic formula, which is the following. So I just wrote here into the script. So you import NumPy just to do some quick calculation. Well, actually here it's not even needed, so well, just remove this. This is, for example, some peak data that I just took from the curve. So this is the peak 1, peak 2, peak 3. And if I just do peak 2 minus peak 1, I get the time in between those two. And if I want to get the distance, well, I want to know the speed at which it travels through the medium. So if this is sound which travels into air, well, this would be the speed of this. So here it's water, so maybe I'm kind of wrong here, so I would have to recalculate this. But anyway, this is just to tell you how to do this. So the distance is equal to the speed multiplied by the time, right? This is one of the most basic formula that you learn in high school. So the distance here is equal to the travel velocity of the sound wave multiplied by the total time, which corresponds to the difference between the two peaks. And you have to divide this distance by 2 because you have a back and forth on the wave, right? So this is 2 times actual the distance to reach the obstacle. So if you want to know distance from your sensor to the obstacle, just use this simple formula and you get the distance. So I'm doing all of that just to explain to you how it works. Of course, in real life, simulation, sensor design, everything would be automated. You wouldn't have to think about all those stuff. You just put it into a script, you calculate, and you get your measured distance and the different characteristic of your sensor pretty quickly. So that's I hope this video is useful, at least for some people watching this. So thank you very much for watching.